mic and camera test, we would like to request everyone, if you can actually see and hear us from your end, please confirm by sending us a thumbs up on the chat box. Okay, thank you so much. Right, that's cool. That's great. Okay. All right, thank you so much. And then, yeah, just a little bit, yeah, just for the housekeeping, for you to be able to focus on this webinar, we would like to request to disable all the notifications so that you can have a laser focused attention on this webinar today, okay? And then the instructions are on your screens. Okay, and then if you have any questions, please feel free to post it under the Q&A function on the top right-hand corner of your screens. All right, thank you so much. And for those who have been asking, okay, for common questions and FAQs, so for everyone who have registered, everyone will receive a copy of the PDF slides as well as the link to the video recording within the next 2 business days, okay, via email. So please monitor your junk email folder. And then, yep, so for those who will stay until the end of this webinar, we will be providing a certificate of attendance for those who have stayed until the end. Okay, and there will be a link or QR code that will be posted that will direct you to the survey, so that you'll be able to, you need to do the survey before you can actually receive one. Okay, once completed, we will try our best to send it to you within the next 4 business days. All right, thank you so much. And for those who are new here, for the first timers who have attended this our webinars here at EIT, a little bit of EIT. So we are an engineering specialist from the name itself, Engineering Institute of Technology. We focus on providing courses to our students. We deliver professional certificate courses, diplomas, advanced diplomas, undergraduate certificate, bachelor's, graduate certificates, graduate diplomas, master's and doctor of engineering courses. Okay, so these programs are industry-oriented programs and has a world-class accredited with a world-class accreditation. So our vocational programs and higher education degrees are accredited or registered by the by the Australian government, as well as recognized under the 3 international engineering accords, namely Dublin, Sydney, and Washington. So these programs are being delivered by industry experienced lecturers, okay, they have been highly experienced engineers and subject specialists with applied knowledge. Okay, so these programs as well are being delivered through a unique delivery model, which is making use of live and interactive webinars. Of course, with our international pool of expert lecturers, dedicated learning support officers, and state-of-the-art hands-on workshops, laboratories, and simulation, remote laboratories and simulation softwares. Okay, so why students choose EIT? Because as you can see on your screens, yeah, we're top one in terms of the satisfaction, students' overall satisfaction in postgraduate engineering programs. We also ranked top one in the full-time employment for undergraduate engineering programs, and top three for both quality education experience undergraduate engineering programs and student support for postgraduate engineering programs. So this was based on the KILT survey done 2021, 2022, and 2023. Okay, and in 2024, we have been awarded as the export award for international education and training. Okay, as you can see on your screens. All right, thank you so much. And for today's topic, that would be a study on innovative pin-connected structural system for large span steel structures, which will be delivered to us by Dr. Jian Wei Ma, who's with us today here, and then he will be introducing himself later on. And yep, so without further ado, I will give the floor to Dr. Jian. Dr. Jian, thank you so much.
Thank you.
Would you be able to take control of the screens, Dr. Jian?
Yeah, I tried.
Okay, it's on the top.
Yeah, I see it.
Yep. Okay, that's it. Okay, got it. Thank you, Dr. Jian.
Okay. So
Yep, you may
my
start now, Dr. Gian.
connection, yeah, my connection not stable. Okay, sorry, everyone. Good morning, good afternoon, and good evening to everyone. Thank you, everyone. Thank you, everyone, to be here. And also, I would like to thank EIT and thank um, my supervisors as well. My supervisor, Anna, Milan, and Professor Haddad. Uh, I'm going to have a brief introduction about myself. Um, I'm a structural engineer in Australia. Also, I'm a chartered engineer and registered engineer in Queensland. Um, Apart from that, I'm a registered structural engineer in China as well. I just graduated from EIT. I completed a doctor degree and maybe just a couple of months ago. My research focused on innovation structure system. And excuse me, Marvin, I can now see the slide.
Yep, I can see your slide, Dr. Gian.
Okay, apologize for my maybe connection.
Yeah, we would like to apologize to everyone. Actually, if you cannot actually see our faces on the screen, we are trying to resolve that one. But Dr. Gian will be here to discuss, and hopefully you'll be able to see the screens while Dr. Gian is actually discussing with us. Thank you.
Okay, I do my best. Sometimes it come up, sometimes it disappear. Um, okay, my presentation I'm going to divide it like 5 parts. Firstly, I'm going to have a brief introduction about my research background, and then I'm going to introduce the design process. And after that, that followed by some experimental study and the finite element analysis. And lastly, I give some like recommendations and draw some conclusion. So firstly, I'm going to give a very brief introduction about my research background. So as you can see from here, this image shows like a very typical project from our client. And in recent years, our client going to build already build some of this kind of a project, and this kind of project have some specific requirements. Also, is different from like a typical traditional building. And this kind of building have like a big span from 35 to 50 meters. Also have like a very high floor to floor height, a roughly from 15 to 27 meters high. And that's one floor height equal like office building, like a 5-story height. And so apart from that is against like a highway level load, and the level load from 15 kilonewton per square meter and to 25 kilonewton square meter. And also compared to office building, it like 5 times as office building. Slightly bit lag. I need to move. very slow. So there's some very specific requirement from the client. The client apart from safety design, to comply with like international, especially local standard, another very critical requirement is that sustainable design. The client asked for like reuse or reassemble this building maybe after built in a couple of years. They're going to remove everything and rebuild this building. So the client expect to reuse all most of the members and not recycle, reassemble all the members in a different area. And so this kind of requirement a big challenge for us. This diagram shows for traditional steel structural system, we can see in more like a flow chart. And this is traditional steel building and can be assembled and disassembled. But after built, not easy to reuse or reassemble everything. If you're going to reuse all the members, you need to like cut the connections, which the client is not happy with. And they would like to reuse the whole members. This slide shows some very traditional solutions. As we all know, traditional solutions include like rigid connection, semi-rigid connection, and pin connection. Maybe some country called it simple connection. This is a very typical three types of connections we used for the steel structure system. For this kind of building, we also have some like possible solutions, such as concrete truss and post-tension concrete beam, as well as composite beams and columns. But apparently, like a concrete material, it cannot be like reused or reassembled. So this figure shows like popular connection for the truss to column system. Uh, as we mentioned before, is similar to beam to column connection. Also, we use the truss connection, like pinned connection and semi-rigid connection and the rigid connection. In this, during the design process, we compared if for this kind of span, and we definitely use the truss to column this kind of structural system. And we compared pinned connection and fixed connection to the column. There are a lot of advantages for the pinned connection. Pinned connection is easy to install and easy to assemble and disassemble, and the quality is easy to control. But on the contrary, is the fixed connection. the quality, because there's so many weld to the column and between the members. So the weld quality is very difficult to control. We need some like high skilled laborers. Also, the cost is higher than pin connection. So this figure, figure shows that we conducted analysis just for like a very simple portal frame. If we use a pin connection for beam to column, this kind of structural system that cannot work well. If we use a pin, under the lateral load, such as earthquake and wind load, they got a big deflection. If there's no bracing in this structural system, that cannot work. But regarding truss to column, this kind of system, as we can see, a pinned and fixed, there's no much difference between pinned and fixed. So the deflection is very similar. So the stiffness is also almost the same. So that means use the pin connection for truss and the column. That's no problem. These photos shows us like typical details. Some like in real world. From these photos, we can see there are too many bolts for the connections. Actually, for this structural system, if we design it bolted and wired connection, there are likely more bolts for each connection, roughly like between 30 to 40 bolts for each connection. So there are too many bolts. It's very difficult to install, and the quality control not easy. Also with high labor fee. So, is there any new solution for this kind of structural system? We did a lot of research. We explored some options. From the right side of the slide, here shows some looks very different connections. It's called pinned connection. It's more like a ideal pinned connection. This kind of connection can only resist axial force. It cannot resist a moment, especially the out of plane. There's no moment, just the rotation for this kind of connection. Sorry, sometimes I'm struggling to move the slides. I cannot see the slides. So I need to wait a little bit for the response. The response very slow. This photos also shows some application regarding interconnection, such as the Singapore flyer. It's like a big Ferris wheel. If you go to Singapore, you can see this connection. Also, some pin connection and was used for bracing. because here I'm in Australia. If you come here, you go to Sydney Harbour Bridge, you can see like a huge pin connection. And if someone in Western Australia, there's like a bridge, use the pin connection for the column. As we can see, at the bottom slide, there's some pin connection for the column. Also between the beam, the column, the base, all use the pin connection. Excuse me, Marvin.
Yes, Dr. Gian.
I cannot move. I cannot see the slide. I just like
Okay. All right, let me just take control again, okay?
yeah, like attachment there. There's
Mm. And, which
no
slides are
slide
you in?
showing up.
Okay. Which slides are you in already, doctor?
I just saw like attachment there, but there's no slides showing up.
Hmm. That's weird. Just a sec.
Yeah.
Okay. Slide 20. Are you in slide 20 now? Oh, sorry.
Yeah,
That
I
was
think
from the
so.
chat. Okay. Can you take control
Yeah.
again? Um, Dr. Jian, can you take control of the slides again, Dr. Jian?
Yeah, there's no slides. I just I can
Okay.
see the name of the the
Mm.
file, but there's no slides showing up.
Oh, okay. Let me just a sec.
Um,
Just a sec.
maybe I can re-enjoy. I just leave.
Yep. No,
I
no, no.
try.
I think. Can you see the slides now?
No.
Still not. Oh, it's weird. Mm. Or maybe you can you share the slides from your end, Dr. Jian? Is it possible?
Oh yeah, that's much better, I think.
Yeah.
Yeah,
Yep.
I
Can you
try.
please do? All right. Cool. Thanks.
Yeah. Sorry for the audience.
Mhm.
So can you guys see my slides?
We can see your screens. Maybe you can just put that in presentation mode.
Yeah. What now?
Yep, I can see that one. How about our attendees? Can you see the screen now? Can you send us a thumbs up, perhaps? All right. Yep, they can actually see that one. Yep, you can proceed now.
So
Thanks.
okay, can see my slides. Okay. Is that page 20? Okay.
Yep.
I'm continue.
Yes, please. Thank you, Dr. Jen.
Okay, sorry for everyone. Okay, let's continue the second part, like design process. So what is the pin connection? Is a pin connection originally from mechanical area. It's like widely used in bridges and mechanical, such as like lift cranes, something lift something. Here shows a lift leg lug. It's like composed like a ear plate and a shaft, a big shaft. We can see the shaft as like a big boat. Uh, Also, the red side shows like a lifting lug, or sometimes it's called a pad eye in mechanical area. For this building, we some new idea. We're going to use like truss uh, to the column. There here shows the section, and we're going to use pinned connection for the top chord and the bottom chord, as well as the web. So to connect the column, all the connections like an ideal pinned connection. So as we discussed in previous slides, a similar diagram shows the traditional structural system. And here shows the pinned connection structural system. And regarding environmental performance and sustainability, we can see almost all the members and the connections can be assembled and disassembled. I would say maybe 90% of the steel can be reused, apart from except the column base. Actually, if we design the column as a truss as well, we can use pinned connection for the truss base. So we're going to design this kind of connection. And are there any standard available worldwide, like um, Australia, UK, USA? Fortunately, most of these countries available how to design this sort of connection. But almost all the standards just only design this connection for some simple members, such as for as I showed before, for the column base and for some bracing, not very completed like the whole structural system. And also we found that almost all the standards, the equations, the principle are similar. We can same as the pinned connection for the shaft. We can same it as like a beam supported by ear plate and resist the moment and the shear force. Also, we need to check the bearing capacity. For this building, we build a 3D model by two different software. One software is MyDustGen. It's very popular, used worldwide. Also, another very popular software is SAP 2000. Also, we can use another very popular software called ETABS, similar to SAP 2000. In Australia, we can use Space Gas. After build this model, we find like the critical truss here shows some like extra force, like top chord resist under compression, and the bottom chord under tension. Also, like the diagonal the member under tension as well. So next point, we're going to check if for how to design the pin connection and to resist this kind of force. I'll compare all the standards. We think also European standard is more clear, and the principle is also very understandable. So we designed this pin connection by using European standard. Here shows like a typical detail for the pin connection. This pin connection for the shaft already reached like 110 diameters. You can imagine like a big boat, like a 110 diameter mills. So we designed the pin connection according to standard, but we yet we're not sure. Is that is that safe for the whole structural system? Because there's never have this kind of structural system. I think because I did the research for already like 6 or 7 years. Before that, there's no project by using this kind of a connection for the whole structural system. So we planned to do some laboratory test. Laboratory test is a requirement for almost all the standard worldwide. If there's something, some mechanical behavior is not clear. So after laboratory tests, we need to conduct a finite element analysis to compare the result, to verify and validate the results. Here shows some laboratory test device and some finite element analysis software. Software, I think we all know is very popular one, Abacus, ANSYS. In another one, I didn't list here, it also belongs to Midas gene. It's called FEA, some similar to very simple than Abacus and ANSYS. In Australia, we use Strand 7, also similar to Midas gene, that one. Regarding experimental study, we designed like a 4 specimen. 4 specimen, the first 2 is the pin connection itself, and the third and the fourth one, we like manufactured like a part for the truss. And this specimen will against like a monotonic load and cyclic load. The last specimen we need to subject to cyclic load. So for laboratory tests, there's some loading device. This conducted by like local university. Most of the university had kind of this device. All the specimens, specimen 1, 2, and 3 will subject to monotonic static load. And the last one will under cyclic loading. The device have some capacity, like just 200 pounds. We can see later, we can see some maybe specimen is over the device capacity. After we set the plan, we need some instrument to measure like the displacement strain. So we need some strain gauges, displacement meters. Just something similar for specimen 2, also the same, similar to specimen 1. We use vertical displacement, horizontal displacement meters to the some strain gauges on like on the ear plate and some on the pin shaft as well. Specimen 3 is like a part of a truss. We need more like more displacement meters to monitor the deformation, like a top chord, bottom chord, and the web. So specimen 4 is similar to specimen 3. This photo shows the where the strain gauges, and also some photos shows like displacement meters. Maybe we cannot see it clearly. For the shaft, it's not easy to add some strain gauges because it is hidden, it's covered by steel plate, ear plate. So we need to measure the shaft. Later we can see, because it's a big deformation, we can measure it by like tapes or rulers or something. This is the loading system. As I mentioned early, the first 3 specimen will against monotonic load, like three stages. We need to apply for the load, for the design load, ultimate load, and like yield load. And for the last specimen, we need to against like a cyclic loading, like a tension, compression, back and forth. There's some testing results regarding specimen 1. It have like a big capacity, and compared to design load, the safety factor is more than 2 times into the design load. And after this connection failed, it failed mainly because, as we can see circled here, the quality of the weld. If the quality of the weld is better, this connection have a bigger capacity. The second specimen against compression load. For pin connection, compression load have better capacity than tension. Actually, for the design, a compression is not critical. But during the experimental process, there's something we can see the photo here. The ear plate like touched the end plate. So looks like the ear plate has some support. The last part of deflection for the shaft will be not accurate. Let's talk about the specimen 3. Specimen 3 is like a truss, under tension force is behaved much better. I think much better than a single pin connect. I think because the truss with connection and the overall behavior is much better than the single pin connection. So we can imagine if a pin connection be used in the whole structural system, the whole structural system will, I think, of course, can have much better than the truss. The last specimen is a little bit complex. It's need to resist like cyclic loading. Under compression, I think because of the manufacturer defect, there's something like buckling occurred. We can, from the photo, we can see in the flange buckled and deformed. But for this specimen, we focused on tension behavior. So from the curve from this curve, we can see tension part is very smooth and very rounded. So indicate that it have good ductility and effective energy dissipation. So that's the testing result. Next, we are going to compare the result by element analysis, by finite element analysis. Here we shows some like model created by Abacus. There's some creative factors for finite element analysis. One factor is the friction. Friction coefficient is really hard to decide how much we're going to use. It's most popular factor is like 0.2 to 0.3. And also the some contact pair definitions have a big impact on the results. Before we conduct finite element analysis, we need to use, here shows the material mechanical properties. We need to use the same properties as the testing. And these properties also conducted in the laboratory. We tested some like samples, got the results, and put these results in the finite element analysis software. Here shows some results for specimen one, the first one. We just showed some part of results, and because we need to get the results under design load, ultimate load, and the failure load. Here it just shows some of the results. We need to get the stress and strain and the deformation. Also, for loading, we use the same stages as laboratory test. And we divided into 3 stages. First one is design load, and then ultimate load, failure load. Regarding the shaft deformation, we can see we got the similar results in just the 0.7 mils, and consistent with the test results, 1.2 mils. That's minor deformation. Similar to specimen, and we got the results for specimen 2. Specimen 2 is under compression force. Also same as laboratory test. We use 3 stages, same force. So we got results we're more focused on the shaft because the shaft deformation is critical for the connection. And this one, as we mentioned before, finite element analysis, the shaft and deformation just like 6 mils, but the laboratory like doubled, just because the ear plate, have some attachment to the end plate. Specimen 3, also we use the same stages. And we need to, during the modeling, we need to define the contact and the coupling. We got the stress results, and the strain, also some deformation. So the finite element results align very well. But for specimen, just limited to the first half stage, and the rest of stage 2 and the stage 3 not align very well, and a major reason is that during the laboratory test, there's some eccentricity, some force to make the whole process a little bit not accurate. The last one is the very complicated one, and this sample will subject to cyclic loading. We need to put tension and compression. For example, we start from like 20 ton. We need to negative 20 ton, positive 20 ton, something like that. And gradually we got 120 ton. Same as the previous specimen, we got the stress, strain, and deformation as well. For the last specimen, we can see the results strongly align with experimental results. Also, we got like a big capacity, like more than 100 ton kilonewton. And also there are some deviations between finite element analysis and the testing results. I think just because for the real sample, is there some manufacture defect, also some maybe the quality of weld. But for finite element analysis, like some factors, contact factor, and some like some factor we need to adjust a little bit, can cause different results. Also during the laboratory testing, there's some out of plane, like a twist, rotation, something to impact the displacement meters. But overall, here we compared finite element and the testing results. We can see from here, the first, second one, and the third one is very, have a good agreement. The last one, as we talked previously, for tension area, we can see it had a good agreement as well. but for compression, a little bit different. This is the comparison of the like automate loading and the design loading. We can see all the specimens have a large safety factor, more than 1.5. Some of the 3 times of design force. So in summary, all the specimens have a big safety factor that can meet relevant standard, and the shaft, the pin shaft, the deformation that very minor, just like between 1 mil to like 2 mil, like 6 mils. And the second specimen is a bit different because there's some minor errors during the test. And finite element analysis verified or validates the testing result. According to the comparison, we have some recommendations because the weld quality is very important. So during the construction, we need to enhance weld inspections. Also, we need some like mixed extra stiffeners for the truss. Another recommendation for the pin, because the pin shaft can move, we need to fix the both sides. So lastly, draw some conclusion and give some suggestions. The pin connected this kind of structural system shows like good seismic performance, have a good ductility and dissipation capacity. Some recommendations such as strengthen ear plate thickness and improve the quality of the weld. Overall, is have a very good agreement between the design force experimental results as well as finite element analysis. So these results can be applied to a similar structural system in the future. Next, for some future research, I'm going to conduct like a multi-scale model, maybe by use MetaSgen software and by Abacus to compare the results. Some details such as for construction, because currently there we follow the mechanical requirement, and there's some minor gap between the ear plate and the shaft. It's very difficult to install. Maybe for future, we can increase the gap. Also, next time, I'm going to do some research on sustainable design by using, for the column, using truss as well. Therefore, the whole structural system, she can assembled and reassembled very easily. These photos shows some completed projects in recent years, like train station, stadium, and the convention center. You can some truss for the roof and for the floor framing as well. Okay, that's my presentation. Thank you, everyone. Any questions?
Thank you, Dr. GN. So, yep. So, just put the screen on. Dr. GN. So, for those who have been asking about what courses covers this topic, so as you can see on your screens, we have the professional certificate course of competency in structural design for non-structural engineers. We also have the advanced diploma in civil and structural engineering, and then we also have the advanced diploma in civil and structural engineering focuses on material testing. We also have the online bachelor's in civil and structural engineering, and as well as online masters for civil and structural engineering. So Let me just share my screen here. Just a sec. By the way, thank you so much, Dr.
So
Gian,
this,
for that one. Let me just share my screen.
yeah, I stop sharing.
Yep. Yes, please. Thank you. Okay. Just a sec.
Yeah, some
So, yep, I think you're still sharing your screen.
it looks the freezed.
Let me see.
Can you stop it? I cannot do it.
Okay. Still on you're still on the screen. Okay.
Yeah, no,
Yeah,
it's
still on the screen.
freezed.
Okay. Sec. So yeah, we also have our upcoming courses. Webinars. So yeah, I can still see your screen.
Yeah, because of freezed.
I'm not sure what's happening, but okay. But anyway, I can share my screen. Let me see. I'm not sure what's happening. But anyway, yep. Thank you so much for those who have attended. I'll be posting the link on the chat box. Just a sec for those who. But before that, let's answer this one question here. Dr. Gian, he mentioned, did you observe much? Did you observe much shear locking in the results? That's coming from one of our attendees today.
Here, it's like
Mm.
shear force.
So yep, he was actually asking, did you observe much shear locking in the results?
Yeah, we not focus on the shear. We
Mm-hmm.
only focus on the because I think the shear not very critical. Because from the standard from the calculation,
Mm-hmm.
and we got a big shaft and a big ear plate. The
Mm-hmm.
shear capacity is massive, so we just focused on the
Mm-hmm.
tension and a little bit of compression. Yeah, the
Mm-hmm.
tension most critical.
Mm, I see. Okay, I hope it answers your
Yeah.
question.
Okay.
And we have also one from Ahmed. He was any
Mhm.
comparison, Dr. Jin, any comparison of results with various other standards, UK, Australian, and US? So
Yeah,
that's coming from Ahmed.
that's another topic. We compared. We use all the standard. Got all the results. Um, is there some minor, differential between all the standard? Because all the principle is the same. We need to check the shear force, the bending, and the bearing. And it's just the factor because of the different country, the safety factor is different. So yeah, we do have some comparisons. Not share here, not sharing here. Am I right? Can you hear me?
Oh yeah, sorry, I'm actually muted. My apologies for that. So again, thank you so
Ah,
much, Dr. Gian, for that wonderful presentation. And then for those who have attended today, again, we apologize for the delay. We have encountered some issues with the platform, and then thank you so much for patiently being with us until the end of this presentation. So yep, I have posted on the chat box the link to the to receive the certificate of attendance. So you can just fill out the form, and then you'll be able to receive the digital certificate for today's webinar for certificate of attendance. Okay. Thank you so much. Any words of wisdom, perhaps, Dr. Gian, for those who wanted to study to be in the civil and structural engineering field?
yeah, thank you, and feel free to contact me. I think I have some email address on my slide. You can contact me anytime. If you got any questions, just send me an email. Thank you, everyone.
All right. Thank you so much. And I think that's it for today. See you in our next webinars. Have a good one. Bye,
Okay, you
everyone.
too. Bye. Bye.
Bye, Dr. Jin.